Yebo Tutor. Nyasha here. I hope you're well and safe, and I hope you're enjoying your learning period. We are about to finish up a few calculations on chemical equilibrium. We introduced the calculations last week. I hope you had fun with us, and I hope it was meaningful and sensible to you. So what we want to do today is to go through a set of questions that we promised we were going to attend to, which are in one of your question papers from the year 2021. So did you see that question paper? If you did, please just indicate. I think you should have seen that question paper on the stream. So I put it on the chat. Right, so let me just welcome you once again to our Yebo Tutor session, where we are working out some chemistry problems. I just want to switch off something that is making some noise here. Please give me a second. So our first question is on chemical equilibrium. The questions we are working through are all coming from the 2021 question paper. The question paper that we are attempting is available online, so you can ask your friends or your teacher or your parents to assist you to get this. Right, let's also listen to our contributions here, so you can drop in your chat contribution into this YouTube chat. So what I'm seeing here is the question paper that we are working on today. That's the 2021 paper, and our question is question number 6. That is the question that is dedicated to chemical equilibrium. Right, so we will go through each question, and we might have to use some data sheets. So just remember that you always get at the end of the paper, there's a data sheet. So it shows you some physical constants, it shows you some formulae. So in case you've forgotten some formulae, they're provided for you. So life is actually good. Right, so let's get started. So once again, our chemical equilibrium falls under chemical change. I'm sure you've seen that many times now. So let's get to see what we have to work out. So chemical equilibrium, the first question is straightforward. Chemical equilibrium, the first question is straightforward, and it reads, define the term chemical equilibrium. Define the term chemical equilibrium. So what is your understanding of chemical equilibrium? Right, so since it's a definition, I think we just need to focus on what's important. We are looking at chemical equilibrium as a certain stage in a reversible chemical reaction. So your keywords are the fact that in itself chemical equilibrium is just a stage in a certain chemical reaction, but that chemical reaction is a reversible chemical reaction, right? So we've been given that they say we are considering the balanced chemical reaction below. It's a hypothetical reaction, and it takes place in a sealed 2 dm cubed container, which is at 300 K. So the first thing they want us is to just define chemical equilibrium. So the key words in your definition, you should talk about chemical equilibrium as a stage. It's a stage in a what? In a reversible chemical reaction. So every chemical reaction has different stages. There's a stage where you just have the reactants. There's a stage where the reactants start to interact. There's a stage where they form some products. There's a stage where the concentration of the reactants begins to deplete and the concentration of the products begins to increase. Then, if the chemical reaction is reversible, then there is a point at which these reaction rates will become constant, and then your chemical equilibrium has been reached. So this is a stage in a reversible chemical reaction, and at that stage the rates of the chemical reactions, the rates of the forward and the reverse chemical reactions are now equal. That is when we say chemical equilibrium has been reached. So it's either you are discussing these rates that are now equal, or the concentrations of the products, or the concentrations of the reactants. Right, let me just write it below here and say concentrations of the products and the concentrations of the reactants no longer change, right? The concentrations no longer change at chemical equilibrium. So it's either these, the rates of the chemical reactions are now equal, or the concentrations of the products, the concentrations of the reactants remain constant, isn't it? Right, so it's very important to separate issues there. Okay, fine. So I think this one is a definition, and I'm sure you've got even better definitions than me. So you can play around with the correct words there. Remember, they're keywords, right? So these are your keywords. These are your key words, and these keywords are obviously, this one, it's, you need, even if you have a synonym to stage, right? Maybe you are, okay, phase is not an appropriate word, just because it's phase is not, we can talk of phase of matter, right? We can talk of phase of matter. So phase is not exactly appropriate, but it's a stage, isn't it? It's a point at which the chemical reaction in the forward and the reverse are taking place at the same rate. Okay, fine. Enough of definitions. So last week we carried out certain calculations that prepared us for this question. Question number, okay, so let's just read it out at first. Right, first of all, we've been introduced to the chemical reaction that's taking place here. Let's just blow this up so that we can see, right, like that. So this is a balanced equation. Remember our procedure from last time. We said every time we need to first check if the chemical reaction is balanced. So because these are just PQ unknowns, right? These guys have already just told us, okay, this is already a balanced chemical reaction. So we're happy. So consider the balanced chemical reaction below for a hypothetical reaction. So it's not a real reaction. That's why I'm saying P and Q are just some unknowns. They are not known elements. It's not phosphorus. We are not talking of phosphorus. Q, I don't know what starts with Q. Right, so this is a hypothetical reaction. It's just an imaginary reaction. It takes place in a sealed 2dm cubed container at 300 K. Right, so after our definition, they now ask us some things that concern that chemical reaction. And they say the amount of each substance present in the equilibrium mixture at 300 Kelvin is shown in the table below. So this is the chemical reaction which took place at 300 Kelvin, and the amount of each of the species are what are shown. 0.8 mole of the P substance, 0.8 mole of the Q substance, and then 3.2 mole of the PQ product, which is a product in the forward reaction. So then the temperature of the container is now increased to 350 K. The temperature of the container is now increased to 350 K. Good. So this is what we are told about this process. The first question is the heat of the reaction. When a new equilibrium has been reached. So this is now at 350, isn't it? Because the temperature of the sealed container was increased. So when the new equilibrium has been reached or has been established, it is found that 1.2 mole of the P substance in its gaseous form is present in the container. So in other words, there was an increase in this substance. This one increased when the reaction was at equilibrium at 350 Kelvin. So in other words, this side of the reaction is actually favored when you raise the temperature. Okay, so I understand the process. The first question is the heat of the reaction positive or negative? Is the heat of the reaction positive or negative? So let me give you let me just say 1 or 2 minutes to figure this out. Is it positive or negative? So we are just going to state, right, positive or negative, because they've already highlighted these words by just capitalizing them. So the question is the heat of this process positive or negative? What do you think? Please state your answer. Please state your answer. Right, so what do you think? Is the heat of this process positive or negative? Right, so since they want us to just write the answer here, let's reason it out elsewhere. So this is where we can start. We can use the information provided in the table and in this change that has been announced. So the process starts, right? So this is our chemical reaction. It said we have 2P, if I'm not mistaken, plus a Q2, which is reversible to form 2PQ. So at 300 Kelvin, we have 2P, so let's say at 300 Kelvin, the amount of 2P is 0.8. And then at 350 Kelvin, the amount of P is now at 1.2 mole. It's now 1.2 mole. So the reason why P increased is that the temperature was increased. So in other words, this is in a sealed container. This must mean that the heat initial, which was corresponding to, right, so MC delta theta, it's corresponding to 300K, right? And then the final heat, so let's say MC times 300K. And then heat final would be corresponding to MC 350K. So this is just our absolute approximation of the heat. So this obviously shows that the final is greater than the initial. So this is what we have in this process. Heat final is greater than heat initial, right? Heat final is greater than heat initial. If the heat final is greater than heat initial, our delta H is actually equal to heat final minus heat initial, isn't it? And if heat final is greater, then it means this is a plus delta H. So if we are to look at this chemical reaction, plus delta H actually favored the growth or the increase in P, and P is part of our left-hand side. So in other words, when the temperature is increased when you deposit some heat into this system, this reverse reaction is favored. Why? Because after this change which we have seen, the species that increased are on the left hand side. So if this reverse reaction is corresponding to A plus delta H, it must therefore mean that the reverse should, which in this case is the forward reaction, should be a minus delta H. So here is the heat of the reaction, positive or negative. We have figured out that the heat is what? Is negative. Any questions on this one? How did we arrive to negative? We simply looked at the chemical reaction. So we looked at the chemical reaction and we said we can tell that at the initial temperature we had 0.8 moles. At the final temperature we have increased the number of what? Of moles of P. It is obvious that according to the temperatures, we know the heat can be approximated by that equation. So according to the temperatures, the final heat is larger than what? The initial heat. So if this is the case, then delta H, the one which we want to find in this question, delta H simply stands for the final heat minus the initial heat. And we can tell that if the heat final is larger, then delta H is positive. So if delta H is positive, and that positive delta H resulted in an increase in the species on the left-hand side, it must mean that this process, which is the normal process from the left to the right, is actually a delta H negative process. In other words, it gives off heat in the forward reaction and therefore is an exothermic reaction in the forward. So we have figured that out by just looking at what's taking place in this process. Now there's a question here, 6.2.2, which states, use Le-Chatelier's principle, or Le-Chatelier's principle, let me scroll down to it, to explain the answers or the answer to question 6.2.1. So what does Le-Chatelier's principle state? What does Le-Chatelier's principle state? You can go read that, or I'm sure you already know it by now, that according to Le-Chatelier's principle, the equilibrium of a chemical reaction that is reversible shifts in a certain direction that counteracts the change in temperature in this case. So the equilibrium shifts in such a way that the reaction that counteracts the change in temperature is favored, isn't it? So that is what is taking place in this process. So how do we then explain the negative delta H according to this principle? So obviously the first thing is that the principle, according to the principle, the reaction, or rather equilibrium shifts, the equilibrium shifts towards the reaction that reduces the heat, right? So in other words, the equilibrium must shift towards a chemical reaction that reduces the heat of the system, or that absorbs heat. Why? Because temperature has been increased to 350. The heat of the container, because this is a container, right? And they said that this is a what? This is a sealed container. So if it is sealed and you deposit heat into that container and you raise the temperature, according to Le-Chatelier's principle, the chemical reaction that counteracts that increase in heat is what is favored. Okay, good. So that is what the principle states. That's point number one. We can see there are three marks here. So obviously we need to find a way and the logical steps according to the principle that guide us towards the negative delta H. So now let's look at, we've said that that is what the principle says. So in this particular situation, in this reaction, in the reaction that we have, in this particular reaction that we have, the equilibrium must shift towards the reaction that reduces heat, isn't it? What has taken place here is that the species that increased with the increase of heat are on the left-hand side. These are our reactants. Increased. So this is rather the quantity of the reactants, or the mole quantity, or the moles, or the molar quantity of the reactants increased with temperature. This is what took place. The reactants increased with temperature, implying that the reverse reaction is, it absorbs heat, isn't it? Implying that the reverse reaction absorbs heat. So the reverse reaction, so implying that the reverse reaction, and what is a chemical reaction that absorbs heat? Because the moment you just increase the heat, then all those species started to increase, right? So as long as that container absorbs heat, then that reaction is favored. So the reverse reaction absorbs heat. Let's just call it is endothermic. So it's obvious, right? This implies that the forward reaction is exothermic. Therefore, our delta H is less than 0. And that is negative. Okay, fine. So we've just picked up the logic here, and we've seen that, okay, so it's important for us to actually think like what's taking place in the chemical reaction, but at the same time, precisely, rather accurately answer the question, right? Accurately answer the question. So using the principle, explain why the chemical reaction is what is exothermic, because you say that the heat of the reaction is negative. So explain why it is exothermic. First of all, state the principle itself and customize it to what is actually taking place in this chemical reaction. So the principle states that the equilibrium of a reversible reaction shifts towards the reaction that reduces heat, according to what is taking place in this question. So the moles of the reactants increased, right? The moles, or the content or the quantity of the reactants, increased with temperature, isn't it? This implies that the reverse reaction is actually endothermic. By depositing heat into this system, the reverse reaction was favored, isn't it? So this must imply then that if the reverse reaction is favored by putting more heat or having the system absorb heat, then that's an endothermic reaction. In other words, the final temperature is actually higher than the initial temperature. So the reverse must be true. The forward reaction, right? If the reactants absorb heat, then the products must actually lose heat. So in other words, the forward direction is exothermic and its delta H is negative. Let's see if that makes sense to you while we go to the next part. So we are going to focus on this question, question number 6.2.3, to make use of all the principles that we learned last week. Remember, we were working on calculations, isn't it? So this is where it's happening now. Calculate the equilibrium constant of this process. Calculate the equilibrium constant at 350 K. So let's see you work out a few ideas on how to calculate the equilibrium constant at 350 K. Right. What steps did you take? Which steps made sense to you as you were calculating the equilibrium constant at 350 K? Point number one, we need to state the actual equation that guides us to find this chemical equilibrium constant, isn't it? Because that's what you want to calculate. When you write the quantity that you want to find, it immediately tells you what is inside the equation that you actually need to calculate, because you might be given some of the things. So there's no point in you starting to rush to put in numbers before you've actually put the equation. That requires you to then look for certain quantities. Okay, so first of all, to calculate the equilibrium constant at 350 K, our equilibrium constant equation simply states that the equilibrium constant must be equal to what? What did we say last time? Do you recall? The concentration of the products raised to their stoichiometric coefficients divided by the what? The concentrations, or the product of the concentrations of the reactants. So in our chemical reaction, I'll just take this page to show us the chemical reaction once more. So this is our chemical reaction. So let's just see it. There we are. This means that our products are called PQ. So this is our product PQ. And we will, first of all, the states, first of all, these are all in a gaseous state, right? So we are happy. This is in a gaseous state, gaseous state, gaseous state. So we're happy. Remember that you can't include species that are either solid or liquid. So our PQ is obviously raised to the power of 2, and then we are dividing PQ by the concentration, or we actually have a product of concentrations this time. So we're dividing by the concentration of P raised to the power of 2 multiplied by the concentration of Q2 raised to the power of 1, which we can just write as that. This is the equation that guides our calculation. So therefore, it means all we need to do in this work, or in this question, is to calculate the concentrations. So that is the objective. So to calculate the concentrations, so let's say the concentrations, use a what? Do you remember what to use? If you want to calculate the concentrations, you have been given, what have you been given? You have been given the initial molar quantities. You have then been given the final molar quantity of one of the species. So what are you going to use to calculate the concentrations so that you can calculate the equilibrium constant? So I think by now you recall that we can use a rise table. Use a rice table. Right, so what does our rice table look like? The format of our rice table is simply, we have some chemical reaction, right? Let's do this. Then we have some number of what? Number of moles at some initial stage. We have some number of moles at some initial stage, and these are in mole. Then we have some number of moles at the equilibrium point. In other words, let's start with the change. We have a change number of moles for the change, so these are moles. And then we have the number of moles at equilibrium, and these are in mole. Then we will have the concentration of the species at equilibrium. In this case, it will be in mole per dm cubed. Let me just rather put it this way, to the -3. So this is our rice table, and then we can now partition it. So these are just units. I'm just showing you the importance of making sure that your calculations are in SI, in the required units or in the acceptable units. So this is our format of this calculation. So you can use other means and methods if you don't necessarily want to use this rice table. Right, so let's state the chemical reaction first. So we have 2pq, 2p, we don't need to write the state or the phase, plus q2, and this will form 2pq. So all we need there are those coefficients. So that's our table now, so we will just demarcate so that we know which is which. So we're demarcating our table. It looks like that. Then it looks like that. So there we are. That's our rice table. Let's also maybe try to neaten this side. And maybe this side. Okay. So that's our rice table, and we can now put in our initial quantities in mole, our change in the quantities in mole, our equilibrium number of moles, and then the concentration in moles. So this means that this this row of concentrations is what we actually need for this equation. So the whole objective of tabulating like this is to systematically arrive at the answer, so that even if a question comes in other shapes and sizes, you are not really stuck at where to start, isn't it? You just follow a certain sequence or a line of thinking. Okay, so let's move now a little bit faster. So what are the number of moles initially? What are the number of moles initially? The number of moles initially for the substance P are 0.8. What are the number of moles for Q2? 0.8. Number of moles for the product? 3.2. That is what we are given. What is the change in the number of moles when this process is taking place? They tell us here that when a new equilibrium is established. So this is very important. When a new equilibrium is established. Why are they saying new? Because all our changes are going to start from 0.8. We are going to say either plus or minus. I don't know what happens there. Then we are also going to start from 0.8. Whether we'll add or subtract, we'll figure that out. And we'll start from 3.2. So this is a very important keyword that they've written so that you can know that you are not starting from 0 as far as the products are concerned, isn't it? Right, so there are some changes that are taking place. So they say when the new equilibrium is established, it is found that 1.2 mole of P is present in the container. So we already have an answer for the first one. number of moles at equilibrium. This is now at 350, right? This is at 350. And then this is at 300. K and K. All right, let's make that a proper K. Right. So that is what's happening there. So we have 1.2 mole of what? Of the substance P at the new equilibrium. What does this show you? Has P increased? Obvious. It was once 0.8. It is now 1.2. So there's an increase in P, obviously, by the appropriate stoichiometric ratio or coefficient. Right. Our ratio, by the way, you can tell that this is 2:1:2. So that's just our stoichiometric ratio, which is why we are using it for identifying the ratio by which these changes will take place. So 0.8 on the 0.8 for Q, 0.8 will what? Will increase by X, isn't it? Just because the coefficient there is 1. Why are we saying it's increasing? Because the chemical reaction, as we can see, is actually favoring what is on the left-hand side. So 0.8 increased by X, and then the products are obviously going to decrease, isn't it? The products are going to decrease minus 2X. So this stoichiometric ratio is very important for you to tell what's taking place. So this is our set of equations that we will use to find the unknowns. So let's look at our equation once again. The equation here is that we want to find the concentration of what? Of PQ. And can you see that we can immediately find the concentration of PQ from this calculation? We can immediately find it because we're already given the ingredients for the equation. So the concentration of P, the concentration of P is actually equal to the number of moles of P at equilibrium, which is the 350, divided by the volume. So this is already something that we can calculate. What is the number of moles? They told us. It's given. So there is no problem here. 1.2 mole. So these are the units that I'm writing there. Divided by the volume of the container. They told us it is a what? 2 dm cubed container. So this is 2 dm cubed. What does this give you? This gives you the concentration of the product P to be equal to our number of moles over the volume. So this is now 1.2 divided by 2. And what does that give you? 0.6 mole per dm cubed. So this is our concentration of P. What are we trying to do here? We are just filling in our rice table. We are just filling in our rice table. So what is the next step? Now that we have the concentration of P, it was readily available, isn't it? It was readily available because they gave us that. So it's found. So we are happy that this part of the equation is already solved. So how can we find the concentration of these now? How can we find the concentration of PQ and the concentration of Q2? So to find the concentration of PQ and Q2, calculate the number of moles. Can you see that? Which is this row. Calculate that row, isn't it? Why? Because we know that concentration is simply number of moles over the volume. The volume is given, so we just want to find the number of moles of Q2 and PQ. Right, so let's determine X, isn't it? Determine X from this. So let's determine X using this first part. We already know that 1.2 is the result that you get when you add 0.8 plus 2x. Then you get 1.2. So this implies that your 2x is equal to 1.2 subtract 0.8. 1.2 subtract 0.8. And what is your 2x therefore equal to? 0.4, isn't it? So what is your value of x? Your x is actually 0.2. Does that make sense to you? What are we doing? We said we want to find now the concentration of PQ and the concentration of Q2 so that we can fill in this part of the calculation. How can we do that? We can do that by finding x, just because we already know what's happening to the species P. What is happening to the species P? When a certain change takes place, then its number of moles become 1.2. So the new number of moles is obviously equal to the sum of the initial number of moles. That's why they said new equilibrium. There's an initial number of moles already, plus 2x. Then we use our basic algebra to come up with the value of x. Now that we know the value of x, this must imply that we can find the number of moles of what? The number of moles of Q2. It implies that the number of moles are Q2. Right, excuse me, sorry. Right, the number of moles are Q2. Right, so let's calculate. Number of moles of Q2, we can find them so let's just add this number first. Number of moles of Q2 are simply equal to 0.8 plus x. 0.8 plus x. And this must be equal to, or rather let's write it here, 0.8 plus 0.2. And this is equal to 1.0. So we now have a number of moles for Q2. Q2 has 1.0 moles. Q2 has increased. Right? Next are the number of moles of PQ. Number of moles of PQ. This is equal to 3.2 minus 2x. 3.2 minus 2x. This is equal to 3.2 minus 2 multiplied by 0.2, which is 0.4. So what do you get? You should get a 2.8. So let's write our 2.8 for the number of moles. Now our rice table is almost complete, isn't it? Our rice table is almost complete. So now let's find the concentration. So therefore, rather, this implies that the concentration of Q2 is equal to the number of moles of Q2 divided by the volume. And what is this equal to? This is equal to 1.0 moles divided by 2, sorry, I should put the units there, and dm cubed. And this must be equal to what? This is equal to 1 divided by 2, 0.5 mole per dm cubed. Right, the same applies to, let me just take this and put it here, right? The same applies to the concentration of PQ. Now, the concentration of PQ being the number of moles of PQ divided by the same volume. This is all in the same volume, isn't it? This is all in the same volume. So this is equal to number of moles. We have already calculated 2.8. Volume, we already know that is 2. This is 2 moles and this is 2 dm cubed. So what is the final answer? 1.4, isn't it? 1.4 mole per dm cubed. 1.4 mole per dm cubed. So let's fill in the rice table. Concentration of Q2 is 0.5. Concentration of PQ is 1.4. Now we are happy because we can continue our calculation now. Concentration of PQ, we're just taking that. So that is a 1,4 squared. Concentration of P, we are taking that 0,6 squared. Sorry, yes, squared. And then multiplied by concentration of Q2, 0,5. Raised to the power of 1. Right, so basically that is how you would use a rice table. Let's just punch in the values. Let's just punch in the values so that we can see the outcome. Right, we have a 1.4 that is squared, and then we want to divide this by 0.6 squared, 0.6 squared, then we will multiply this by 0.5, 0.5. So we are getting 10,888. So that's 10,8 recurring, which we can say, or we can approximate to 10 point. Let's just see the significant figures that were given here. 0.8, one decimal place, 0.2, that, okay, so it's all one decimal place. So let's round it off to 10.9, and it is a constant. It is just a number. Okay, so that's our equilibrium constant in this calculation. Your value should be 10.9. So for those that that have been, let's say, following the calculation, what's important is the equation. Obvious, this equation is very important. If the equation is important, this means the concentrations are going to be very important. The concentrations are going to be important. And how you get there, that involves the chemical reactions. But how did you get to those concentrations? Then the molar changes are going to be important. The molar changes are going to be important, and they are based on the stoichiometric ratios. So you need all the aspects of this rice table in order for you to actually fill in all the values into the chemical equilibrium calculation, thereby getting your answer for the chemical equilibrium constant, in this case, which is 10.9. Right, so let me just hope that as you follow this calculation, probably you have seen one or two ways, isn't it? One or two ways of coming up with the answer. So let me also check. If you come across an equilibrium question like this, are you going to have some trouble? Are you going to have some trouble? Right. I hope not. So let's now just see this question here. I think we'll finish off with this one. Then we'll continue with the rest of the question next week. So by the way, when we finish the rest of the question, in fact, I would like you to finish the rest of the question. When we meet next week, I hope that you will have covered it. Then I will ask you to, isn't it, you can see my number on the WhatsApp chat, the Yebo Tutor WhatsApp chat. So you can just look for my name somewhere there. My name is right in the front of you on the screen. Then you will then write me the question, isn't it? So you write me the question that you may have on the rest of the calculations, because it would be beneficial for us to actually see if you're actually benefiting from here. For those that would want to join our Yebo Tutor program, you are free to join through this link. Let me see if we can share this link. Where is this link? Right, there we go. So you can actually join us on this link, and then you can post your questions now onto our chat group. You can find our details there, and then we can interact and see if your question has actually been answered, isn't it? Otherwise, I thank the student who provided this question. You made it very beneficial for others as well. Okay, so let's now look at 6.2.4. How will the equilibrium constant calculated in 6.2.3, which is this 10.9, how will it be affected when the volume of the container is decreased at a constant temperature? When the volume of the container is decreased at a constant temperature, choose from increases, decreases, or remains the same. Yes, okay. This is very exciting a question. So we'll finish up on 6.2.4. Right, we'll finish up on 6.2.4. Right. So this is where we are, and how? It's very important to answer the question. Answer the question. right? There are many ways, there are many things that you can say about what is taking place here. But their question is simply, how, isn't it? Their question is simply, how is the equilibrium constant that you calculated affected when the volume of the container decreases at a constant temperature? When the volume of the container decreases at a constant temperature, temperature doesn't change, what they do is they squash it, right? They squash it. So let's just see how they can squash it. Let's just see how they can squash it. Is this there's something that I've seen before on this site that can help us. Right, let's just see. Yes, I think it's gases. Yes, it's gases. It's actually this one. Let me actually go to the other simulation. Okay, it's not on states of matter. I just want us to see some gases. I think I can also change this one. So let's just see if it works. So this is just a simulation that is just showing us the reduction of what? The reduction of volume. But this time it's at a constant temperature. So there are certain things that will actually be different from what we're seeing here. So what we are seeing here, okay, hold constant. I want to hold temperature constant. So I think I have to go to the other program. Please just give me a moment. Give me a moment. But otherwise, what do you think? What actually changes? What actually changes? Is the equilibrium constant going to increase, decrease, or remain the same? These are the keywords. Increase, decrease, or remains the same. Then you get your 1 mark. Then you give a reason. Then you get your 2nd mark. Right. So it's also important to actually identify the mark distribution. So I just want gas properties. I think this one I'll be able to discuss what we want to see. Yes, I think we will. Right. So let me share this link. So please try this out. Please try this out. So reduce volume at a constant temperature. Right. Reduce volume at a constant temperature. Let me just see if we wrote the correct spellings there. So reduce volume at a constant temperature on this tool, so that you can see what's actually taking place. So I'll just paste the link. Then you can click the link there. So this is what you're seeing on this simulation. So let's just see ideal gas law. Okay. So there are certain laws that I'm sure you already know, that we have Charles law, Boyle's law, and so forth. So we want to hold. Why don't I have an option? Because I want to hold temperature constant. Okay, so I actually don't have that option again. Okay, so sorry, not gonna work. All right, so in this case, okay, let me just pump. There we are. Good. So the link works. I need to actually run it first. I need to pump the container with some gas. Then everything that we are looking for becomes activated. So I will restart the simulation. I want to reduce the volume, isn't it? So remember, when we restart, we are at some volume, or maybe we can even exaggerate, so that we can start from a situation where there's a very large volume. Then we will pump this container, sealed container. Remember, sealed meaning this one will be shut. So we'll pump this container with some gas. Obviously, the particles will move with some kinetic energy. They rub against each other, and then there's a thermal component to that, and then it is attributable, or you can actually measure that temperature. So now we're already at 300K. Our container has some gas, so I'll just run some more particles there. Then the pressure is rising. So we're just increasing the amount of gas within this container, right? So we are now at 300K, right? We are now at 300K. I would like to just hit this so that we can increase to 350K, which is like what we have in our question. So I'll just increase this to 350K. Let's drop that a bit. Very cool tool, isn't it? You can actually ice it so that you can drop the temperature. Right, 350K, there we are. So we are at 350K now, so our gas particles are having fun, isn't it? Remember our system here, it's full of gases. These are all gases. So this is our reaction, so these are all gases. So that's what we are seeing in the simulation. So they say now, if we keep our temperature constant at 350K, right? We started with a certain temperature of 300K, then we increase the temperature to 350K. Then we want to hold the temperature constant. So when you run this tool, please go onto the hold constant and click temperature. So hold the temperature constant. Now, if you're holding the temperature constant, now let's reduce the volume and see what will happen or what is expected to take place. So temperature is being held constant and we will drop the volume. So when we drop the volume at a constant temperature, right? Let's think about the process. The process that we have seen here, it was affected by a change in temperature. A change in temperature increased the number of moles of certain species. Let's just go to our rice table once again. Look at our rice table. These are the quantities of our species at a certain temperature. Then our quantities of the species have actually increased, right? The number of moles of these species have actually increased on the left-hand side and then decreased on the right-hand side, isn't it? So there's been a change in the number of moles and hence a change in the concentration of these species. So if there's been this change in the concentration of these species, obviously it affects Kc. This is what has taken place already. Now the question is, if we maintain the temperature as it is and then we just reduce the volume, what does that have to do with Kc? Right? What does that have to do with Kc? So without thinking about Kc, this is what we'd expect. So we're now reducing the volume. So the only thing that has changed here is that we can see that, okay, we've maintained the temperature constant, but there's been a change in the pressure. If we go back to our initial state, our pressure is around 9 atmospheres. If we go to some final state, our pressure is now 20 atmospheres. The pressure of the container is what is just changing, right? The species in there are still the same, right? So the pressure has changed. So now let's look at our particular case. If you hold the temperature constant, there is no change in the concentrations of these species. Why? Because we've already seen that this chemical reaction is actually dependent on the heat, isn't it? This chemical reaction is temperature dependent. If you raise the temperature like what happened, the species on the left-hand side increased in quantity, right? So it's just a shift from PQ and then you increase the concentration of what? Of P plus Q. That is what takes place. But if the temperature is maintained as it is, these concentrations, it's now at equilibrium. These concentrations are not going to change. So it actually means that our Kc, which is a concentration dependent quantity, is in this case actually going to remain the same. So here it's going to remain, Kc remains the same, right? And the reason in this case, I think we've already discussed it. So you can now figure it out and put it in your own words. Right, so I hope that this tutorial was making sense to you as far as calculating the chemical equilibrium constant, right? Calculating the chemical equilibrium constant. And you are calculating the chemical equilibrium constant having been given an equation which is just hypothetical. We don't even know what P or Q are, right? These have just been thought out by the examiner and says, okay, this time they want to examine you on an unknown quantity. So while you are practicing on known chemical reactions, there's no need for you to claim a chemical reaction, because these questions can come in all shapes and sizes. So it might even come without a single symbol of a chemical reaction, of a chemical element, like in this case, they are all hypothetical. So P is not even phosphorus, isn't it? Okay, so I hope that as you follow this tutorial, you will be able to now attempt the next question. So this is now for you to have fun. 6.3 is now for you to have fun. You can carry out that calculation and finish off the rest of the questions. If you still have some points that are not clear that you would like highlighted, as far as these last two questions are concerned, please interact. Otherwise, next week, I also want you to interact with us on the chat. Please tell us next week, would you like us to work out the equilibrium question from the 2020 paper, or rather go and finish off our acids and bases? So you tell us, then we will come up with our decision during the week, and then on Friday, next time, same time, then we can have some fun. So there goes today's tutorial. I hope that you had some fun coming up with your rise table. Otherwise, that is it for me, from me for today. Enjoy the weekend, and let's meet next week. Right, there we go. That's today's work. We've covered part of, rather an important part of chemical equilibrium. An important part of chemical equilibrium. Thank you. Have a nice day.